Well, hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am very happy to have Veronika Dornan and Bill Harris with us today. Hello, Veronika. Hello, Bill.
Hello.
Greetings.
Veronika, let's start with you. Hey, that's a very lovely library behind you there. I gotta admire that. Bill's got one too, so you guys both admirers of libraries there. So very cool. And Veronika, what's your geolocation? Where are you located at?
So I'm here at McMaster University in Hamilton, Ontario.
Okay. Is fall going in the air? Or are we still
A little bit. Yeah, still a bit hot, but we have a few leaves that are starting to turn yellow. So
Oh, ooh, okay. Awesome. And Veronika, where are you in your trajectory?
so literally, yesterday was the first day of classes, so I'm beginning my final year of my PhD. So I'm aiming to defend sometime next summer. And I'm just starting to get into postdoc applications right now.
Well, let me be the first one then to congratulate you, Dr. Dornan.
Not yet. Not yet. Next summer.
Close enough. Close enough. And Bill, you are in McMaster as well.
Yes, at the moment I'm sitting at home, but yes, we're pretty close to the same geolocation, within a few kilometers, I'd say.
Okay, very cool. So it is September 4th of 2024 as we record this, and I'm in Phoenix, and we're still in our summer mode. We will still get up into the 108, 110s Fahrenheit here over the next couple of days. In fact, I was just reading something this morning. We've had 100 days of 100 plus degree weather in Phoenix this year.
Oh.
Yeah, it's warm. But it is cooling off. It's getting a little cooler in the morning, so very good. And Bill, what do you like to do for research?
So, very short detour. Way back, I started as a grad student as a theoretician, astrophysicist. I came out of a mathematics degree, pure math, no physics, no astro, just pure math. And I thought, okay, I'd like to do astrophysics, but I must be a theorist, so I'll try that.
Okay.
But after a year of that in grad school, I just got my master's, and I thought, there's other people around in the department who are working on these things called globular clusters, and they're taking beautiful images, and
Yeah.
that sounds kind of like fun.
Cool.
So I switched. I kind of pulled up traces on the theory side and moved into the observational side. And I started having way more fun with all that. And eventually started working on globular clusters in our own Milky Way galaxy. But then after some years, I thought, well, this stuff around other galaxies sounds interesting too. So let's try that. And fortunately was able to start getting observations that were relevant and helpful, and kind of kept moving further and further out in distance and bigger and bigger galaxies. And so still fun.
Great. And I think today we're going to do a little combining of a little bit of theory anyway and some observations. So it'll be cool. And Veronika, what do you like to do for research? And how about the topic of your PhD thesis?
Yeah, so my thesis is specifically on the relationship between globular cluster system total mass and total halo mass for galaxies, which has been observed for almost all galaxies we've been able to get this observations for. So my thesis is focusing on that. So I do observations of globular cluster systems around really massive BCGs, but I'm also very interested in where dwarf galaxies lie on that relationship as well. And as we're going to see in this paper, how to kind of methodologically improve our ability to get estimates of these globular cluster system masses and distributions and radial profiles.
Yep. Very cool. And I can't beat that introduction. So that's going to take us straight into this article, to this very lovely AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Utilizing Voronoi tessellations to determine radial density profiles. And Veronika and Bill, take us away.
So, Veronika and I settled, maybe I'll just comment on the background for this and where it came from. So let's take half a step back and just imagine a two-dimensional surface with points scattered all over it.
Okay.
just points here and there and everywhere, not in any regular pattern, but just kind of anywhere. And one of the things that's important for a lot of application is we would like to know the number density of those points,
Yes.
maybe as a function of where we are on the plane. Maybe there's some overall pattern. Densities are higher in one area than another area.
Okay.
But maybe it doesn't, again, follow any regular pattern. Maybe there are different centers. Maybe there's a radial distribution around one center. Maybe there's another center where there's other points. And how do you turn all that into numbers? How do you quantify that?
Yeah.
Well, so there's the classic method, which we refer to sort of halfway down on the introduction to the article, where you take a center point, and you think of the number density, you draw a series of little annuli around that center point, and then you calculate the number density of points in each annulus, and then you draw some kind of curve of number density versus radius.
Yep.
So, and so as we say there, this annulus fitting method is useful in its simplicity, but it doesn't work if it's not so geometrically simple. What if there isn't any underlying geometry that makes it symmetric?
Okay.
And what if there's more than one center? Or what if there's no center at all? I mean, what do? We would like to be able to have a way to determine densities of points that doesn't rely on any geometric assumptions about the distribution.
Yes.
So at that same time, I had just been reading about Voronoi tessellations, Voronoi cells, dividing up a plane into these cells where each point is enclosed by a little polygon that consists of all the parts of the plane that are closer to that point than any other point. And so you think of the plane as divided up into all these polygons, and there's one point in each polygon.
Yes.
And so that was the idea. I mean, we could calculate the density of points all the way down to, it's so local that we can talk about the density of just one point.
Yes. Right.
Which sounds a bit paradoxical. How do you, but you've divided up the plane now into all these polygonic cells. And so the density applied to each point is just the inverse of the area of that cell. And so you have the density of points in the most local possible way, one point at a time. And then you can decide how to plot up all these numbers. Now you have many, many more numbers to work with than you had for just kind of these big annuli, or assuming that something follows a simple radial distribution.
Yes.
So then I brought these over to Veronika, and I just kind of dumped all this raw material on her lap and said, okay, we've got potentially a way to calculate, distributions of points that is potentially more powerful than this classic annular method, which is useful and simple if the geometric situation that you're applying it to is also geometric and simple.
Yes.
But if it isn't, then we've got a tool to do something better.
Cool. And also, of course, if it does have a geometric center, how do the two compare? Right?
Yes, exactly. And so we talked about this, and Veronika had lots of raw material that she can talk about next, and away we went.
Cool. Awesome.
So, yes.
Very cool. Okay.
So yeah, so if we go to figure 1, we can kind of see a comparison of these two methods that Bill was kind of talking about. So in this paper, essentially, it was the question of, okay, what will this method look like? How do we make a Voronoi tessellation plot and then get densities for it? And then how do you make the radial density profile for it? So that was like one part of it. But then the other part was, okay, yes, this will definitely be a method that will be more useful if you have complex systems that are not symmetric or have multiple different centers. But let's walk before we can run. That's like where we want to apply this. But in the simplest case, when you're just comparing these two simple methods, if you just have one system, it's circularly symmetric, there's no kind of other contaminants, which one will return a better estimate of the underlying distribution. So that was exactly what we did. This is an example for one of the systems we created. And essentially you can see on the left, in kind of the fainter blue circles, you divide up the image into these concentric annuli, and the darkness of each of the annuli corresponds to the density associated with that annulus.
Gotcha. Okay.
So these are what we're looking at here in Figure 1 are simulated distributions. We'll get to the real things later, but what's been done here is to generate a random distribution following an overall radial profile. And then, as Veronika said, absolutely right, we got to walk before we can run. So we'll start with a classic simple situation where we can actually compare the old classic method with this newer method in more detail.
Good, perfect.
So one of the things that you can immediately notice between the two plots of the exact same system on the left with the annulus, on the right with the Voronoi, is right off the bat, you get a lot more information about kind of local density for each of these objects. So on the left of the annulus method, in the innermost region, the kind of density of those innermost two annuli, it doesn't get that dense. The color map between these two plots are exactly the same. And you can see for the annulus method, it doesn't reach that darkest density that it does for the Voronoi plot. And it also smooths over a lot of the kind of individual fluctuations, which in this case, because it is just a symmetric, simple distribution, these are just stochastic scatter. But you can already imagine how different this would be if there was actual, different types of structure within this system that you actually did want to know information about. So there's a lot of interesting applications to this method, but we'll focus right now on just simply which one of these will return a more accurate estimate of the distribution.
Yeah, and let me ask a question while we're on this as well. Is each one roughly about the same computationally, expense-wise? Or
Yes.
the annulus take 1 second and the tessellation takes hours?
No, yeah, they're essentially exactly the same. These tessellations are not difficult to create. It's roughly exactly the same. Yeah.
Okay, good. Thank you.
So this is just one of the kind of systems of objects we created. So in the paper, even though for us, we work observationally with globular cluster systems, ultimately, that's what we want to apply this to, but the benefit of this method is it can be applied to really any system of discrete objects. So it can be applied to stars around a globular cluster, for instance, as well, or any other kind of system that you'd like. So we kept things kind of broad in this paper. But if you scroll down to table 1, it kind of outlines the different systems that we created, all of them just, still just a Hubble power law underlying, but with randomized distribution of objects. So varied kind of the sizes of the systems, the number of objects within them, all giving them the same kind of size, maximum radius. So really just varying kind of the density of them. So our smallest system was only 300 objects, so a very, very small system. For us, because we work with BCGs, this is still more globular clusters than Milky Way has, all the way up to a system with 20,000 objects, which is to the size of some of the BCGs that we work with.
Okay.
And as you can see, we also varied how big the kind of core of the Hubble distribution was and what that innermost density is, and the exponent as well. So we get kind of a lot of different Hubble profiles that you can kind of compare to. And yeah, right there in equation 1 is our definition of the Hubble profile that we used.
Yep, cool. I'm with you.
So in order to kind of create this Voronoi tessellation, we're able to get density values for each of the tessellations, because there's only one object in each tessellation, as Bill said, you can just invert the area to get an individual density for every object, and getting a radial value from the center is just as simple as we have the XY coordinates, just calculate it.
Yep.
But this we found resulted in, as much as we would like as much information for every system in order to get individual densities for every object, there is such a thing as too much information, because of course there is stochastic scatter.
I was gonna say, right, there's got to be
Yeah, so if we go down to figure 2, we can kind of walk through each of the kind of bins that we did this in.
Okay, we're gonna zoom out, and well, actually, we're gonna zoom in and thinking too,
Yeah.
one individually. Okay, let's do that.
So here is for the exact same simulated system as we showed above in figure 1. We compared what values you get for the annulus and what values you get for the Voronoi. And the annulus it's kind of hard to see actually in this plot, but they're the little red points. Yeah, you're showing your cursor. So there's not too many of them. Whereas compared to all those blue points, which are the Voronoi tessellations, there are a lot of them. The black line is the fit to those Voronoi tessellations. The pink dashed line is the fit to the annulus, and the green line is that underlying distribution that we want to get as close to.
Got it.
As you can see, both of them are pretty off.
Yes. And let me ask one other question.
Yes.
How many annuli do you take in the annuli method? Because presumably you could take 1 or 10,000 or.
So in this case, we take about, I think we did 25 annuli, or around there. This is pretty similar to what is typically done for galaxies or globular cluster systems of similar sizes that we've kind of worked with.
Okay, good. Thank you.
So yeah, so there's a lot of scatter in this, and it's not fitting as well as we would like to the underlying distribution. So we're going to do a little bit of binning here, not as much as we do with the annulus method. So essentially what we do is we take every object and we go through starting from objects with the highest density, so the highest local density, down to the lowest local density.
Yep.
And we group them together with either into groups of 3, 5, or 7. We compared them to see where can we optimize the least amount of scatter, but still keep a lot of information from these individual data points, because obviously that's what we would like to do, and keep individual information.
Got it.
So in this top one, it's just 1 object per cell. We've done no bidding.
Right.
If you scroll down, you can see with 3 objects,
Ooh, much
right away, things get quite a lot better.
Yeah. Much cleaner.
Now the Voronoi and the annulus fits are essentially overlapping, but they're still, especially in the inner region, overestimating that Hubble density profile.
Yes.
If we go to 5 objects per cell.
Okay, does it go down even more? It does.
It does. So now it is getting a lot closer to what we are hoping to get, which is the underlying distribution.
Okay.
If you bump it up to 7, though, you now get diminishing returns, and the fit doesn't improve significantly.
Right.
So we settled on 5 objects per cell as being a good compromise.
Fair enough. Very good. Okay.
There was another kind of curious question. In this whole process, we learned a lot about Voronoi tessellations themselves, and of course, there's a really big literature in mathematics and statistics about Voronoi cell analysis that we had no idea of before we started all this. And if you think of all these polygons distributed around the plane, it turns out that one part of this vast literature that we kind of dug into just a little bit is that on average, each polygon has about 6 or 7 sides in a typical Voronoi tessellation.
Okay.
They're mostly not squares.
Yeah.
They're mostly not 12-sided things. Most of them are kind of 5, 6, 7-sided polygons.
3, 4, 5, 6. Yep.
Yeah, you can, of course, you can do that by brute force just by getting in there and counting sides for each of those. But it turns out people have actually done all that. And there are even little distribution functions that have been published about, about number of cells versus number of sides per cell, this kind of thing. So
Right.
the averaging that we settled on is sort of grouping 5 cells together at a time, turns out to be almost like the number of adjacent polygons that each polygon is connected to.
Okay.
If that makes sense.
So. Yeah, I'm with you. Yep.
One of the other kind of interesting statistical things about Voronoi tessellations that we learned about through the process of this was potentially an issue that Voronoi tessellations sometimes have, where they can somewhat overestimate the number of very high density objects. So this was brought up by I think Eric Peng and Bill Chen at Northwestern. They kind of alerted us that, hey, this might be something that you should look into. So we did.
Cool.
And what we found was, if you, I think, go to equation 2, I believe.
Let's go to
the previous page.
2 and
yeah, 2.
Yes.
So we found was, again, statisticians and mathematicians have already been looking into this question. So for a random, spatially uniform 2D distribution of Voronoi tessellations, this is the important part. It's completely uniform distribution. It can be described by equation 2 and 3, depending on if you're looking at area or density. And these are kind of complicated equations, but essentially what they're saying is your distribution, your histogram of the densities of all of these cells in a uniform distribution can be described log normally. And essentially the average of that kind of probability density profile of the distribution is a little bit bigger than the actual true normalized density of all of the objects in the distribution. So if you essentially, what this means is, if you make a Voronoi tessellation plot of a spatially uniform, random distribution of objects, it will say that it will return more high density Voronoi tessellations than there really should be. That's essentially what that's saying.
Yep.
So we said that's a problem if it's applied to our method. We don't want to overestimate the density. But our method is not being applied to a random distribution of objects. It's being applied to a Hubble distribution of objects. So we did the exact same thing. We tried to plot up the kind of histogram of cell densities and fit to it. And we found that it is different than for a uniform distribution. So in an ideal world, the average from the probability density profile should be the same as the black line. A normalized density, the average true density is 1. For the blue line, this is for a random distribution, and it's kind of average from that, as you can see, is 1.4. It's larger than the true density. But for our systems, we have a different kind of profile. We have the red curve, and its average is the red vertical line. So it's actually a little bit lower. It's about, I think, 0.9 or 0.95. It varied a little bit in between different size systems. But in general, it is much, much closer to the true density. And the amount that it differs was small enough that for just fitting the profiles, the difference, it was overwhelmed by just stochastic scatter. So it wasn't a big issue.
Cool.
So this was really good for us. We also found out that if you do this with 1 object per cell, you get a bigger difference. You get it to be like 0.8. But if you bin it by 5 objects per cell, you get 0.9. So this is another kind of benefit of us binning together the Voronoi tessellations. It reduces this statistical bias.
Yeah, very good.
Yes, and it's probably worth saying at this point that I mean, we were using a Hubble profile, which is a simple radial profile that describes elliptical galaxies
Uh,
and halos pretty well. The advantage is it's simple. It's basically a power law with a central core, with a flat central core.
yes,
And there are lots of functions out there that
we'll
kind
do
of do the
this.
same thing. So I think this is just it's a particular case that applies to galaxies pretty well. But if we were to use, say, a Cersich profile, which is also a
Uh-huh.
standard one, we'd get very similar results. So I think this is fairly generic. We'd
Yeah.
get the same thing coming up. But it's just that when we move from a random uniform distribution to a radial distribution with a radial profile, then that actually does change this systematic bias back to something that's really quite close to
Close.
not being a problem. So
Yeah, that's great. So it shows that it's actually working.
Yeah.
yeah,
That's good.
So if we go down to the next figure, you can see again for our kind of it's
Okay.
essentially just the 5 grouped objects per cell plot I showed you earlier, just zoomed in so we can get a better look at it.
Okay. I like
So
that.
yeah, so we're able to compare our fits for the annulus and the Voronoi method to our underlying distribution. And we're able to do this for every single one of the simulated systems we did with, as I said, varying sizes and Hubble distributions. So then once we were able to do that, we wanted to actually compare the 2 methods.
Okay.
And we essentially just wanted to ask very simply, there are 2 things that we want to prioritize in terms of how well our fits are.
Okay.
One, how accurate is it? How well is it returning the underlying fit that we gave this?
Yes.
And 2, how precise is it? What is the uncertainty associated with our fit?
Okay, good.
So in terms of accuracy, it's actually kind of difficult to compare our fits with the underlying Hubble distribution just based on the radial profiles.
Yeah.
One, because our underlying distribution, as Bill said, is a Hubble distribution, but we actually are fitting using power laws. So the reason for this is, as you actually may have noticed in figure 1, we do not have any information about objects within the core of
Oh yeah, because it was whited out. Yeah.
yeah. So this is because, again, you know, this methodology can be applied to a lot of different astronomical systems, but for us, we're coming from observing extragalactic globular cluster systems. And when you get down to the innermost radii of the galaxy, the intensity of the light is just too much, and our photometry programs can't pick out any globular clusters. So when we're working with observations, we have no information about that innermost region.
Okay.
We're fairly certain, you know, because it follows a Hubble distribution, that there is a core, but we don't have any information for it. So we typically fit power laws.
Okay. Good.
So that's one of the reasons. The other reason is obviously there's a really big difference in the number of data points being used for both methods. So what we decided to use in terms of comparing accuracy is what we end up using these power laws for in our case, which is integrating them and getting the total number of objects in the system return.
Okay. So it's an integrated measure.
Yeah. So the next plot, we essentially did a box plot for both methods across all systems, asking how well does it return the number of objects that we put in. We know how many we put in.
Okay.
So ideally, we want everything, if it's returning the exact number we put in, to lie exactly along the purple line. It is returning 100% of the objects we put in. Anything above the purple line, it's overestimating. Yes. Anything below, it's underestimating.
Okay, cool.
And so going left to right, we're going in terms of increasing system size, the number of objects we put in.
Yes.
So the smallest system was 300 objects. And as you can see, you know, small number statistics, there's quite a wide gap. I should also say we got these box plots by running each system 30 times. Because we had different random seeds for the same underlying Hubble distribution.
Yes. Okay.
So for system 1, it's only 300 objects, small number statistics.
Yep.
Both give pretty wide spreads.
Okay.
Both, they're around. It's pretty wide. Like neither one is necessarily doing phenomenally
Good
over.
job. Right.
But as soon as we go to system 2, which was a pretty big jump to 2,000 objects, you can immediately see there starts to be a difference. And that difference just continues as we get to larger and larger systems of objects, to the point where when you get to your 20,000 object system, our biggest one, the Voronoi tessellations are sitting quite close to 100% with very much smaller spread. And the annulus method is actually overestimating by about 10%. So the takeaway for this plot is...
Go ahead. Go ahead.
Yes. So the takeaway for this plot is essentially small systems of objects around, a few hundred, probably not a big difference in terms of which method you would like to use. But when you get to much larger systems, as the ones that we use, we look at with BCGs, all of a sudden the Voronoi method does seem to be returning more accurate estimates.
Indeed. And let me ask one question. We got a couple of blue and red dots here.
Yeah, so these are the outliers. So these are just one random seeded run of each system that just happen to lie completely outside of the interquartile ranges for the box plots.
Gotcha. Thank you. Okay, cool.
So,
astronomers always ask about the outlying points in a graph.
Always, because it's where the interesting stuff is.
Exactly.
Yep.
But you have a good explanation for us. That's good.
Yeah.
Okay, very good. So it's working.
So that's promising for accuracy, yes. For precision, we kind of compare it in, I believe, the following table where we get all of our kind of bootstrapped fits of these different systems. So each of these are 5,000 iterations of bootstrapping for both methods.
Okay.
And essentially, I'll sum this up so you don't have to look too closely at all the little teeny tiny uncertainties on this table. But in general, we compare precision in terms of the uncertainties on the fitting parameters for both methods. And essentially, it is a similar trend. In general, the smallest system, the uncertainties are much larger as we get to larger systems, more numbers of objects to work with. We reduce our uncertainty in general. Again, for our smallest system, the difference in uncertainties is not that big. But then with every subsequent system, the uncertainties for the Voronoi method start to really kind of outpace in terms of lowering them compared to the annulus method. So again, with the Voronoi method, our uncertainties are also lower. So for massive systems, it tends to be more accurate and more precise.
Cool. Very nice. Beautiful. Beautiful work. Okay.
So the last kind of question is, okay, this works well for simulated systems, but what about the real thing?
Yeah, let's do that.
So the previous paper that Bill and I published was looking at 11 globular cluster systems around BCGs. So we already had the fits using the annulus method. So then the question was, okay, let's try this Voronoi method for a couple of them.
Yeah.
So these two we picked because they had the least amount of contaminating objects, and they were the most circularly symmetric, because obviously when you apply this to real systems, they can have satellite galaxies, they can be very elliptical, they can have weird artifacts on the images.
Yep.
So we chose these two because they seem to be the closest in terms of what we were creating with our simulated systems.
Right. Okay.
And the results are actually a little bit surprising because for systems of this size, we would expect the annulus fit to return a higher number than the Voronoi fit. But that actually was not the case with these two. So for one, our most massive galaxy, this one at the top, I showed people this plot when I first made it, and they said, "Did you accidentally plot the same
Yeah, I was gonna
curve?"
say.
No, they just happened to both basically return the same distribution.
Yeah.
So their total numbers returned are also very, very similar.
Okay.
So, but a system of this size, we would have expected the annulus fit to overestimate. So that was kind of surprising. The galaxy on the bottom is a bit smaller, but still we would have expected the annulus method to probably overestimate. But in fact, it is the opposite. The Voronoi method estimated the higher number.
Right.
For both of these situations, the uncertainties were still much lower for the Voronoi method than the annulus method, so that was still good. But it was kind of surprising that it didn't quite line up with what we were expecting based on the simulation results.
Right.
Potentially one of the reasons for this has to do with the fact that the steepness of the curves are a bit different than what we would expect for those biggest galaxies that we simulated in this paper.
Okay.
So potentially, there's a situation where when you have a really, really high steepness in the innermost regions,
Yeah.
the Voronoi method is actually better able to kind of more accurately return that steepness than the annulus method, since it has less data points to kind of fit to that innermost region.
Gotcha.
Yes, and I think that's really because this is the advantage of defining very local number densities. With the Voronoi method, you can get down to small sub areas of your whole plane. And with the annulus method, well, you've got a big area that you're kind of, you're trying to calculate a mean density in, and
Right.
You're averaging over a number of things. But again, that's the whole point of the Voronoi method, is you can define very local number densities.
Cool. That makes sense. Okay.
Ultimately, though, the total number of globular clusters and as a result, the total masses of these systems, they were still within uncertainties for what was originally determined using the annulus method. So it's not like we're completely getting a wildly different value, which is what we would expect. Both methods should roughly return similar system sizes. But it was interesting, and it raised the question of, okay, we should probably apply this method to a lot more observed systems to better understand what's going on here, which is exactly what we're doing for our next paper.
Very good. Well, we're going to cover that. Very cool.
But yeah, so yeah, these are the fits and the total number of objects for these two galaxies. And yeah, as you can see, they are within uncertainties of each other, but at the same time, you can see for the Voronoi method versus the annulus method, that number of objects and the uncertainty is quite a lot lower. So that's a big advantage.
Cool. Very nice.
So yeah, just as a summary, this is a really interesting kind of new way to apply Voronoi tessellations, which people in astronomy have been using for a lot of other reasons already. And it's definitely going to be interesting to see how potentially other people want to apply this method. I've talked to some people who study observations of individual globular clusters that said that this might be an interesting way to look at the distributions of those open clusters as well. So it'll be interesting to see how people utilize it.
Yeah, very cool. Very nice. Beautiful work. Veronika and Bill, I want to thank you so much for walking us through your very lovely article.
Thank you.
Pleasure.
Yeah. And you touched on it a little bit there toward the end. So let me push on a little bit. And where do you think we go from here, given the published article? Are there other tessellation methods that might be worth taking a look at? You already mentioned the plan to do it for more than 2 of your BCGs, so let's do it for 100 and things along those lines. So just sort of next steps, where do you think we go with the methodology and testing it on larger systems?
So yeah, so I actually, hopefully in the next month or two, we're gonna submit another paper where we apply this method to the rest of the BCGs from our previously published paper, as well as I think 16 more very massive ellipticals.
Nice.
So this is going to be interesting because these galaxies, some of them are very, very elongated and elliptical. Some of them have a lot of satellite galaxies.
Good point. Good point. Yeah, yeah. Because there are some
And
cases where the annulus method may just fail, right? You're not symmetric enough.
yeah. And it's also
Yeah.
sometimes, especially with those ellipticals, sometimes it's difficult to get a good handle on what the semi-major to semi-minor axis will be when you use annuli. Whereas as soon as I plotted up with the Voronois, it was like, wow, we have so much data to be able to fit this to.
Good. Makes sense. Yes.
So this is something that we're going to be looking into. In addition, the Voronoi tessellations can also be really useful when you want to remove contaminating systems. So as I said, for BCGs, they have a lot of satellite galaxies, and the satellite galaxies have their own globular clusters. And the question is, okay, if I have some globular cluster in my distribution, okay, does it belong to my target galaxy and I want to count it, or does it belong to the satellite galaxy and I don't want to count it?
Yep.
So right now, the standard kind of way to deal with that is just to draw a circle around your satellite galaxy and just ignore everything inside there, which is fine. It's a perfectly fine assumption, but at the same time, we want information about that satellite galaxy as well. So it's the ability to have that high kind of local density information for each object can be really helpful if we want to be able to come up with a statistical method to determine probabilities of an object belonging to one system or the other.
Cool. Very cool.
So that's something it's a bit longer term that we're working on as well.
Yeah, and there's looking further downstream. So it turns out that there's a kind of deep underlying, I wouldn't say an issue, but just a feature of Voronoi cells, Voronoi tessellations, which is if you want to get the not just the density within that cell, but also the uncertainty in that density. How do you do that? And it turns out for the Voronoi cells, it's statistically kind of not possible to do an uncertainty in the density from first principles.
Yeah.
Okay. So that's not a fatal flaw because we can estimate those uncertainties just from the scatter around those radial profile curves that we've been looking at. So in a practical sense, that's not a handicap in a way. But we can also start looking at other methods like a nearest neighbor kind of distance that also there's a literature on where it's now more possible to write down an uncertainty in each estimate sort of from first principles. And we're doing well with this Voronoi method, but we can look into other directions as well.
Yeah, so I might as well run the one that's working and easiest first before making it. So
exactly.
Very good. Very cool. Well, it'll be really exciting. Go ahead. I'm sorry. Go ahead.
No, it's just throughout working on this paper, Bill and I, we're not statisticians, but very much we have had to learn a lot about statistics and the nitty-gritties of it as well to kind of make this paper as good as it is.
Very nice. And it is a nice one. Very cool. Well, I really look forward to seeing this field develop over the next couple of years. It'll be exciting to see your next article. It'll be exciting to see people apply this in different regimes and as we flesh it out a little bit. So very cool. Very nice. All righty, and that will do, everyone. And I hope this made your tessellation astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Okay. Thank you.
Thanks.